In Boulder, Colorado, I wish everyone a good morning and welcome to the EOL seminar series. To inaugurate another year of seminars, I am very pleased to introduce our speaker, Professor Chantal Staquet, from the University of Grenoble Alps in France. Chantal received her PhD in fluid mechanics at the University of Grenoble Alps and crossed the Atlantic Ocean to do her postdoc at the University of Washington with Jim Riley's group. Currently a professor at the University of Grenoble Alps at the Laboratory of Industrial and Geophysical Flows, Chantal is the founding director of the International Master's Program in Environmental Fluid Mechanics. She is also the associate editor of the journal Environmental Fluid Mechanics. Professor Staquet's resume of current research covers two themes: climate change and air pollution, both intertwined but on different scales, and highly relevant and important realms of atmospheric study today. In her presentation, Professor Staquet will examine the meteorology over the very region where she lives, the Alpine Valley of Grenoble, an area where weather and pollution meet and can be a volatile combination, as we shall hear. We are using Slido to pose questions, which you can type in at any time during the seminar. The Slido window is located below this presentation screen. Do not panic if you do not see your question pop up immediately, because we are archiving all questions until the end of the speaker's presentation, where they will be revealed during the Q&A portion of the talk. Professor Chantal Staquet, we welcome you to NCAR and EOL, and the virtual stage is now yours.
Thank you very much, Jackie, for this very nice presentation. Let me start indeed. So I'm going to discuss, as you can see, and as you said, about the atmospheric circulation in the Grenoble Valley during winter and associated pollutant transport. And we are going to see why we are interested in this topic. So what I'm going to present is the major part of the PhD work of Enzo Le Bouëdec. And Enzo defended his PhD 1 month ago, on the 3rd of December. And the work of Enzo was co-supervised with my colleague Charles Gemel from the National Centre of Atmospheric Science in the UK. So let me first present the valley system. As you can see from here, Grenoble is located on the west side of the Alps, and it is the biggest urban area in the French Alps, with about 500,000 inhabitants. Crucial to what we are going to say, it is composed of 3 branches, which form a kind of Y-shaped valley system, and Grenoble is actually located in this basin-like, I can say, topographic feature. And you have a figure here of Grenoble you have a figure here of Grenoble during a polluted episode when particulate matter called denoted as PM later is dominant. So as we are going to see a little later, PM actually contributed in Grenoble for 2/3 by residential heating associated due to wood combustion, and about 1/3 to traffic. So the motivation of this work is exactly this one, is the fact that Grenoble suffers from particulate PM pollution. And what you have here is the weekly PM10 concentration over about 8 years. And there are different time scales, but still it allows you to understand that indeed Grenoble is a polluted city, despite the biggest effort, many efforts, which have been made by the different local authorities in order to decrease the pollution. So the dashed line here corresponds to the World Health Organization annual guideline, and this is the most recent guideline, as you can see. The number is 15 microgram per cubic meter. So despite here there is a weekly time series which is presented clearly, we are always above this annual average, this recommended annual average. And there is indicated here the daily threshold in France, which is recommended of 50 microgram per cubic meter. So despite this figure represents the weekly PM10, you can infer from that there are many days where actually this concentration exceeds this threshold of 50 microgram per cubic meter. It is not quite surprising because PM in Grenoble is dominated by wood burning, that there is a seasonality in PM concentration with higher levels in winter. And from now on and through all slides, the winter period we consider will be indicated in gray and corresponds to the 15th October to 15th of April. So this is our winter season. And there is also high variability in winter with intense pollution episodes lasting several days. Before continuing, I would like to remind you, maybe for some of you, some elements of atmospheric dynamics in mountainous terrain and arrive at why basin, a mountainous basin like this are polluted when urbanized. So usually we distinguish two types of effects which are induced by the terrain, depending upon whether the wind is strong and at large scales. It can flow over the topography, be deflected by the topography or channeled through the topography. Or as you know well, they can be when the large-scale flow is weak. Dominant or the dynamics is controlled in this situation by thermodynamical effects. Let's consider wintertime, winter night. Then there is an infrared emission, so long wave radiation by the ground when it is cooling, which then through conduction and turbulence it cools the air layer above the ground, which flows through gravity, and this leads eventually to downslope winds. So this downslope winds fills, if I say this in a simple way, fills the valley so that there is an air layer inside the valley, which is denser than the air layer which may exist in a plain nearby. Of course, in the plain nearby, there is no such downslope wind, so there is a cooling indeed of the ground, but it's only the ground itself which cools through infrared radiation, and this leads to a very thin layer of very cold air. So eventually you have a thick layer of cold air inside the valley, a thin one into the plain. This creates a pressure gradient and eventually leads to a down valley flow at night. And this system of downslope wind along the slope, down valley wind along the valley reverses during daytime, becoming upslope and up valley flows at daytime. So as I said previously, you have the formation of a cold pool inside the valley, which is associated with high atmospheric stability, leading to reduced vertical mixing. The fact that there is a topographic depression like a basin, and we clearly see here in the situation again in Grenoble, this is a different view of Grenoble, then there is a sheltering effect by the topography from the large-scale flows, and this also results in limiting horizontal transport. So if there is an urbanized, if there is a city inside at the bottom of the valley, then emitted pollutant will accumulate at the valley floor so long as the cold air pool persists, leading to air pollution. So the motivation of this work is the following. It is actually part of a larger project about pollution in the Grenoble Valley, whose name is Mobilair, and there was a logo actually on my first slide of Mobilair. And this project has three main axes to understand the pollution distribution in the Grenoble Valley, and this was what we are interested in order to understand the health effect of particulate matter on people, of course. And also there was a socio-psychological, through surveys, I would say, component of the project in order to determine levels to reduce pollution. So let me come back to health effect of PM. They depend, this health effect, on the exposure of people, but to background pollution and other long time scales. And this is the key point I wanted to stress here. So if you are interested in pollution distribution, in order to be able to infer from that the exposure of people, strictly speaking, you should be able to characterize the spatial distribution of PM in the Grenoble Valley, the place we consider, over a long time scale. So you understand already that this is a very difficult task. So we are not going to solve it, but address part of it, and you will see how we'll proceed. So the question I ask is, how is it possible, would it be possible to characterize the spatial distribution of PM in the Grenoble Valley over a long time scale? Let me first remind you that background pollution is controlled by emission and also meteorology. So to simulate background pollution at the scale of the valley, we need, because we are interested, we must know the atmospheric circulation in the valley for a long time, so let's say a few years. So we need long runs, and of course, I'm going to speak about this later, but when you do a simulation, in order to infer the atmospheric circulation in the valley, if you want to have information about the distribution of PM, emissions should be included as well. So at the moment, I'm focusing on the atmospheric dynamics aspect, where I want to be able to have simulations of a few years, so long run are required. But since we want to simulate the Grenoble Valley, this implies that fine scales are required. So what do we mean by fine scales? Well, you see here topographic representation of the Grenoble area for two different horizontal resolutions. One is 2 kilometers, which is a typical operational forecasting resolution, and this is a high resolution at 10 meters, at 100 meters. We see, and this is what I would like to stress, we see already that at 2 kilometers, the topography is very poorly resolved. The reason for that is that the largest width of the valley is about 6 kilometers. So you could already infer that 2 kilometers is not appropriate, but I think it's very useful to see indeed that it is not appropriate. Now, why 100 meters would be okay? Why not 200, 300? Well, as we are going to see a little later, you have to make a trade-off between the fact that you are interested in a situation you want to have a fine resolution, I would say, along the vertical. So the height of the first mass point should be as small as you can, as small as possible. Yet you have slopes because this is a mountainous terrain. So there is a trade-off between the slopes and the vertical resolution close to the ground, which eventually leads to the fact that the horizontal grid size may be equal to 100 meters. If you do that, then this valley here is solved by 50 points, which is something which also is reasonable. So this means that fine scales are required, and I try to understand quickly why 100 meters. Clearly, we arrive at two incompatible constraints from a numerical point of view. Long run simulation of a few years, fine scale. So how do we do that? How can we do that? So the idea is to rely on the well-known concept of weather types, and we will focus on winter because this is the periods where the pollution concentration of PM is the highest. So the aim would be, is, I would say, from weather types to identify episodes that are representative for wintertime. I'm going to explain what I mean by representative. Then to characterize the atmospheric dynamics for each episode using high-resolution numerical simulation. I just said what I mean by high-resolution simulations. And eventually, because this is what we're interested in, is to evaluate the resulting spatial distribution of PM concentration in the Grenoble Valley. So this is the first step, to identify representative episodes using a weather type decomposition. So this weather type decomposition has to be designed So what are the desired characteristics or properties of this decomposition? First, there should be a limited number of weather type, because as you understand, the idea is for each weather type, assuming the variability inside a weather type is not too large. I'm going to come back to that. Then you can select a few episodes and model them numerically. So find that is the atmospheric circulation in the Grenoble Valley associated with each episode, and from that infer the pollutant transport, the pollutant distribution of PM. So there should be a limited number of weather type. Second point is that in a valley like this, as I said previously, there is this diurnal cycle of up valley flow and down valley flow, up valley wind, I should say, and down valley wind. So clearly we would like to have episodes which are larger than one day in order to filter out the diurnal cycle. So they should be persistent and at least over 2 or 3 days in order to filter out this cycle. Now, this is a key point in the sense that we would like to have a low variability at the local scale for each weather type. The point is the following. Since the weather type will be made of episodes, and episodes, let's take an example. The anticyclonic blocking regime is a weather type. So inside this weather type, you have episodes lasting 1 week, 2 weeks, 3 weeks, associated with the anticyclonic regime. And you would like that when you do a simulation of one episode, it is associated with the characteristic local atmospheric circulation. That is, all episodes of your weather type lead locally to the same, to similar local atmospheric circulation. And like this, I will be able to say that for this weather type, I have this local atmospheric circulation associated with this pollutant transport. And then assuming your weather types are able to span the whole winter weather, I would say, then you are done. Of course, this view is oversimplistic, but this is the idea. So for each weather type, that is for each episode of a given weather type, there should be a low variability at the local scale in this sense that it corresponds, there is a local atmospheric circulation, a characteristic one associated with the weather type. And it follows from this that there should be a low variability as well at the large scale for each weather type. That is, episodes should all be similar, implying that a weather type should correspond to an identified large-scale circulation. Okay. So there is a classical approach which has been used first by Enzo, in the sense that there is a promising approach, promising in the sense that it may answer actually what we are looking for at large scales, at synoptic scales in the literature. And let me use my slide. I think it's better. So it consists in the following. First, as you can see, a very large domain is considered, North Atlantic and Europe. And there is a field which has to be chosen, which is representative of, I would say, the large-scale atmospheric weather. And people most often, but this is also what Enzo did, he chose the geopotential height anomalies at 500 hectopascal from reanalysis, so-called Z500, so it was hourly data and over a 40-year period. Then you may know this, because each field is very large, then you have to apply a reduction of the dimensions of this field, and people usually use a principal component analysis, a PCA analysis, and then you apply, so in the present case, Enzo kept 22 components per field, and then once you have all these fields for all hours over 40 years, you perform a clustering. And here a k-means algorithm was used. And when you do this type of clustering, you have to impose the number of clusters namely the number of weather types you want. And Michelangeli et al. In this promising approach, I would say, they choose 4 weather types. So Enzo redid the analysis. He adds local data to the clustering input in order to have the method being tailored to Grenoble. The reason for that is that here all parts, I would say, of this very large domain are treated in the same manner. So the idea was to say, well, we are focusing on Grenoble, let's add local data to the clustering input before performing the Keynes algorithm. So what is found is the following, and this is actually the same result whether you add or you do not add local data. Adding local data allows the 4 clusters to be a little more well-defined. But the reason for which this approach was so successful is that when you choose 4 weather type, then you recover the 4 typical situations at large scales, which is the winter anticyclonic blocking, the Atlantic ridge, and the North Atlantic oscillation with the negative and the positive phases. So we may say, okay, so we have 4 weather types. We know that in each weather type, the episodes which contribute to this weather type are persistent. So this seems to be okay. And fortunately, there is a high variability between episodes within a weather type, and therefore, consequently, there cannot be any characteristic local circulation associated with each weather type. The fact that there is a high variability between episodes can be illustrated here. What you have here is a snapshot for 9 arbitrary episodes of the winter anticyclonic blocking weather type. So I remind you, weather type is made of episodes, for instance, in France at the moment, and in Europe actually. So there is an anticyclonic episode which may last for 3 weeks apparently. So this is one such episode which contributes to the to this wintertime anticyclonic blocking. So here you have 9 episodes. I'm going quickly because this is obvious. There is a snapshot for each of the 9 episodes from this weather type, and you see indeed that the pattern, considering the Z500 pattern, are completely different. So indeed, there is no, there is a large variability within this weather type, and this is the case for the others. So this means that working at very large scale, at synoptic scales, in order to be able to find weather type, is actually not appropriate. So does it mean that it is not possible? Not quite. The idea now is to say that, well, the key point for us is to have a weather type being associated with a local circulation. Then why not looking at local data? And since we are interested in PM10 distribution eventually, why not looking at local data involving PM10? So this is what is done here. So try to have, again, kind of weather type decomposition based on local data. So what is plotted here is the PM10 concentration as a function of atmospheric stability and local sea level pressure. The reason for which these 2 variables have been chosen is because we know that when there is high pressure, and actually when locally the regime is anticyclonic, there is an accumulation. Of pollution from day to day, and the 2. This has been shown in different papers. The 2, I would say, main parameters, meteorological parameters, are the sea level pressure and the atmospheric stability, which is measured here by the temperature difference between the valley floor, a station located at the valley floor, and a high altitude station. So all of this is based on local data. There is no numerical simulation yet. Okay, so when you look at this briefly, what do you recognize? So this is the background pollution in microgram per cubic meter, and you see that the pressure is high and the atmospheric stability is high as well. Actually, 0 implies that there is an inversion. in the valley, I can tell you that the high altitude station is located 1,500 meters above the valley floor of the Grenoble Valley. So this regime, for instance, corresponds to anticyclonic regime in Grenoble. Clearly here, there is no atmospheric stability, and it is not longer, the atmosphere is no longer stable, the sea level pressure is low, so very likely the PM concentration is very low as well. Very likely this corresponds to a situation where it's raining and there is a storm possibly coming from the west and bringing rain. So just to say that we understand this pattern. So the point we may ask that we understand this pattern, and we may wonder whether it's not possible actually to decompose this pattern into a sub-pattern, each associated with a certain level of PM. So one may wonder whether there are no linear threshold, a threshold in temperature, and a threshold in pressure, leading to the definition of 4 quadrants. More or less, there would be one here, and another here, and another here. So this has been done by Enzo, or the work actually has been done by Enzo. So he used a classification based on the decision tree algorithm. The principle is to find this threshold here in atmospheric stability and in pressure, so as to minimize the variance inside each region here, which we can call a cluster. So this is a kind of pollution regime, this as well. So I could just come back to that. So the classification based on a decision tree was made such as to minimize the variance inside its cluster, and this threshold were defined accordingly once the variance is minimized. So we see that it's not exactly, there is a clear threshold in temperature, but there are 2 thresholds regarding the local pressure. So this defines, as I said just before, 4, I can call them weather type. I would prefer to call them pollution regimes because they are based on the PM10 concentration. Just a few characteristics of this regime. So Enzo called them gamma naught is this one. So it occurs for this situation where this is actually based on hourly data on 7 years, from 2011 to 2011 to 2018. Maybe, yes, it was written before. And these are hourly in situ measurements recorded from winters only, because I'm interested in winters over this period here. So the first regime here accounts, as you can see, for 38% of winter time over this very period I just consider. And it contributes to 30% of PM10, again over winters. And if we compare this so-called gamma PT regime, it occurs only 20% of the time, but it contributes to also 30% of PM10. So so this is the remotest I made. It contributes to 30% of PM10, while being nearly half frequent than this one, this gamma naught. Okay, so we have again 4 episodes based on the pollution, and we know this is local data, and we know that in order to have an appropriate decomposition, each cluster, each pollution regime should be associated with a characteristic local circulation. So is it the case? So this is the question we address now. First, you have to define, in this apparently complicated, I would say, valley, to define how to determine, I would say, a local circulation in the Grenoble Valley. So this is done again from measurements at 3 stations and using assumptions. First, we assume that the Grenoble Y is made of three perfect branches, and that the flow in a branch corresponds to the flow measured at one station, or if you wish, that the flow measured at one station. So we have weather station, there is one here, here, and here. So we assume that the flow measured at one station is representative of the flow in a branch. Then it's important just to spend 10 seconds to discuss about the convention for notation. We use a plus sign if there is an outflow from Grenoble, and a minus sign if there is an inflow from Grenoble, and a zero value if the flow is nearly quiescent, namely when its wind speed is smaller than ½ meter per second. And finally, a local circulation is therefore represented by a set of plus, minus, and zero. And we first mention the circulation on the west branch and east branch and south branch. And for example, this local circulation will be a plus, minus, minus. We follows from this that there were 27 local circulation modes due to the fact that there were 3 branches in 3 states. So this table is a little complicated, but let me briefly explain it. The objective is to understand, is to investigate whether there is a link between the local circulation and the pollution associated with these gamma regimes. So what is plotted here are the most frequent circulation mode. You remember that there were 27. Actually, the most frequent in the sense that they occur more than 1.5% of winter time. So their occurrence over winter time are indicated here. And we only retain those circulation modes, we can call them like this, which occur more than 1.5% of winter time. And here are the pollution regime, and I reminded you the values we find previously about their wintertime frequencies. This is the low pollution regime and the high pollution regime. And as you understand, what is plotted here is the percentage of occurrence of each circulation mode for each pollution regime. It seems to be a complicated table, but a careful analysis, a careful analysis allows you to infer from this that for the high pollution regime, actually, these 3 local circulation modes are dominant. And actually, if you make the sum of these numbers here, they all start with a plus sign, as you can see. They occur 70% of the time during this gamma PT. So it's important to remember what gamma PT is, because I'm going to focus on this regime. This gamma PT is this regime here, which is associated with a high pollution, high stability, and actually to an anticyclonic regime. Of course, this is not local, to a synoptic anticyclonic regime, but over the Grenoble Valley. Okay, so coming back to what I showed, what Enzo found is that 70% of the time for this gamma PT regime, there is a characteristic local circulation which is associated with an outflow in the west branch. Outflow in the west branch means that the flow is going in the west branch toward the north, if you wish. It corresponds exactly to this red arrow like this. And what we can infer from here is that only this high pollution regimes, gamma PT, is associated with the characteristic local atmospheric circulation. So, so we have been able to conclude, we have been able to infer from this analysis that we are able to find a limited number of pollution regimes, but that among these pollution regimes, one of them only, but I would say when we were considering the weather types based on synoptic scales, no weather type was associated with the characteristic local circulation in the valley. So there is a step made. So, so again here, considering this pollution regime, only the gamma PT pollution regime corresponds, as I said, to this characteristic local atmospheric circulation. It involves high pollution episodes. So in the remainder of the talk, what we are going to do is to investigate this pollution regime and, for instance, investigate about its variability. So for this and for this to be done, what Enzo did is that he selected 4 episodes which pertain to these pollution regimes. So this is indicated here. So these 4 episodes, from a practical point of view, they correspond. So I do not want to show you the dates, but 3 episodes corresponds to about 1 week during the December, January 2016 to 17 months, a year, I would say. And there is another episode which corresponds to 1 week in December 2013. So they correspond to specific episodes, given dates in the past, of course. This episode were chosen in order to span, in a sense, to explore the variability of the gamma PT regime. And so what is done here, which is very nice, is that for each episode, the hourly values of PM10 were plotted. So on this figure here. So for instance, E4 corresponds to, as I told you, 1 week, let's say in December 2016. So every hour we have measurements of PM10, and these PM10 values are reported, are overlaid, I would say, on this figure. And when you do this for the 4 episodes, you see that indeed the variability of gamma PT will be nicely explored through the 4 episodes. Okay. So as a second step, so it seems that 10 minutes are remaining only. And I knew I would be a little slow, but I did not know it would be that much. So as a second step, I would like to characterize the atmospheric dynamics within the gamma PT regime. So I need to skip many slides for this. So we are using the word research and forecast model, which of course you know very well. It was version 4.1, using this 4 embedded model. So I don't want to go further. We evaluate the ability of the simulation to reproduce the near surface temperature. This is okay. This is less good in altitude, but we're interested actually at pollutant transport. The fact that I would say that the temperature and the wind close to the bottom are well reproduced, or reasonably well reproduced, is okay. The same for the vertical wind profile. The diurnal cycle and the wind speed trends are well captured, but there is an underestimation of the valley wind intensity. We can still trust the simulation. So if we start, if you remember, the idea is to look at the variability inside this gamma PT episode. So what is done here is that the circulation near the surface is compared for these 4 episodes I just showed you previously. It's very similar. I don't think there is much to say, in the sense that what is actually found is a down valley flow from the east, from a down valley flow from the east to the west branch, and a down valley flow from the south branch toward the west branch. And it's not visible here, but there is a valley exit jet and a recirculation zones. And this is visible in all situations, and this is sketched here. What we do find is something about similar, except that the circulation inside this west branch is nearly inconsistent, but there is still a dominant flow in the west branch, which is actually down valley, and the river is flowing in this direction, and a recirculation zone. So if you look at what has happened I mean, if you average this wind, the flow over the day and night, then these are the characteristics which are found, and the key one being that the day flow persists over daytime in the West Branch. And the second key point, the reason for which it's so similar from one episode to the other, is that these winds are actually thermally driven winds. So, so I don't think I'm going to show this. No, I don't think I'm going to show this. Because the key point for us is to evaluate the spatial distribution of PM concentration in the Grenoble Valley. Just briefly to indicate the emission of PM10. So you recognize the Y shape here, valley. And as I told you, 66% over the year 2016, which is the year for which we have data, are associated with non-industrial heating, namely combustion, and 80% to road transport. This is what I said previously. So what we are going to do now, so I would like to go quickly, but I still would like you to understand. What we are going to do now is to plug, or I would say implement, these emission sources in this domain, as you can see here, and do the numerical simulation for the 4 episodes we selected before. I agree that one episode is in December 2013, yet for this episode, we will use the emission inventory of the year 2016, which will allow us to see the difference associated with the change of atmospheric circulation on pollutant concentration. So this is the simulation which have been done. So now what we have to do is first to compare PM10 concentration as found by the simulation with the one measured. So this is done here. Well, so this is done here for 2 different episodes, E3, E4. Measured is in red, measured is in green, measured is in gray, simulated, should speak slower maybe, simulated is in red. And what do we see? Well, if you want to be positive, you will say that average levels are captures. But it's difficult to ignore that there were intense pollution peaks which are observed. So we have been trying to reduce these peaks. And what can we say? Well, if you consider the transport diffusion equation for the PM, I should say that the PM is considered as a passive scalar here. We ignore chemical reactions. So this equation for PM is simply, I just repeat, an equation which has an advective term, and there is a source, there is an emission, and there is a turbulent diffusion. So we can assume that emissions are okay. They are provided by the Air Quality Agency. They are realistic ones. We may assume that the velocity field is okay too. The comparison, I agree, at one station, but the comparison with the numerical simulations, I would say, are reasonable. So what the problem may come from turbulent diffusion. So we suspected that it may come from the Dierdorf models. So what was done eventually by Enzo is to modify the turbulent diffusivity in Dierdorf models, the turbulent diffusivity of the passive scalar. And if this is done, this corresponds to the green curves. You see that it's better. In the end, the peaks have been filtered out. But I would say the average level have been filtered out as well. And you can see here when what is plotted here is the original, I would say, without correction, of the turbulent diffusion of concentration. So this is the original, and this is with the correction. And what is plotted here is the time average simulation and concentration for one episode, and overlaid with measurements. And you clearly can see that when you are interested in average values of the concentration, it is much better not to implement this turbulent diffusion correction. So in the following, I'm going to consider a simulation with no corrections. But it was still important to discuss these points. So I still have 2 slides. So this is a vertical cross section of the PM10 concentration. So here, this is a star. This is at this location. So this is a cross section across this west branch, and for the square, this is the cross section across the east branch. So what do we see? Well, we see that even if you average over 1 week, you have a clear effect of the anabatic wind during the afternoon. This slope here corresponds to this slope, which is southwest oriented, and this slope here, so it's the opposite, it's southeast oriented, and this slope here is this one, which is south. I'm sorry, I'm trying to go too fast. This is indeed southwest oriented, and this is southeast oriented. Anyway, there is south in the orientation of the slope. So there are anabatic winds, which result in the fact that actually pollution, which is emitted close to the floor, at the bottom, are actually transported along the slope, the one which are exposed to the sun and therefore where anabatic, where upslope winds occur. And this is even more critical, I would say, if you consider a snapshot of PM10 concentration. So this again corresponds to this west branch, and you see that the pollution can actually be transported much higher than 1,000 meters. So to conclude, in a sense, this is now the horizontal spatial distribution of PM10. So this is average over. This is so my time is over. So this is average over one episode. So this is a comparison with between the 3 episodes, and so we see that there were high level of PM10 concentration, which are localized, this high level, at the valley floor and along, I would say, mid-slope, according to what I showed previously. There is a difference between these 3 episodes, but yet we can find that there are 3 PM10 concentration hotspots, which are actually located here, 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 and which are controlled by the topography, and of course by the fact that there are emissions in the valley, but emission are, I would say, elsewhere, and really it's the transport of emission by the local circulation plus the topography which results in this hotspot. And what we see eventually that pollutants are evacuated through this west branch. So let me conclude briefly. Actually, do I have time to conclude?
Yes, you do. Take your time.
So as a conclusion, if you remember, we started by the weather type decompositions. First, it was based on synoptic fields, and it can be shown that a limited number is actually incompatible with finding a characteristic local atmospheric circulation. But what I showed is that there is a large variability inside each synoptic weather type. You remember it was NR plus, NR minus, and so on. So we moved to local data, and there we were able to determine pollution regimes, and actually 4, so limited number of pollution regimes, with one of them at least being associated with a local circulation. So this is the so-called gamma PT regime, which is associated also with the anticyclonic regime over Grenoble, and which accounts for 30% of the wintertime PM10. So we decided to explore this PT regime and selecting 4 episodes which are representative of the variability inside this pollution regime. So we find that there is a characteristic atmospheric circulation near the surface, independent of the episode. The reason for that is that these winds are controlled, are thermally driven wind. They are controlled by thermodynamical effects. And they all present the same features of a down valley wind persisting all day long in the western branch. So eventually, again, in this gamma PT regime, we explored the spatial distribution of PM concentration. So we found that there were high level of PM10 concentration, which are not only confined on the valley floor as expected, but also on the southwest-east oriented slopes, up to an altitude of about 1,000 meters, which is up, I would say, to the plateau of two mountain ranges where people live. And there are also, as indicated here, there are also spatial heterogeneities in PM10 concentration, PM concentration, whatever the episode. And we found that there are three polluted hotspots which exist, I would say, whatever the episode which is considered. Okay, thank you.
Well, thank you, Chantal. This is an excellent study using meteorological observations to its fullest. Here in Boulder, we also suffer from wintertime inversions that trap pollution, and our area also suffers from violating our US air quality standards. So we share similar concerns, even though we're divided by ocean and culture. So we have time for questions. Again, please use the Slido interface located below the presentation screen to type your question. I'm hoping that the audience members are judiciously crafting and typing questions on Slido as we hopefully wait for questions to come in. Can I ask a question? How robust are your pollution regimes? Meaning, if you choose a random number of winters, would the clustering reveal similar regimes?
We considered 7 winters. So, of course, it is not 40 winters, but I still would say there's a large enough number of winters in order to be able to say that the results are robust. Alors, you may not be convinced by my reply. Let me come back to this slide here. Do you see my slide, or should I share my screen?
You should probably share your screen.
Mm-hmm. Ah, yes. Alors, point is that, voilà. Voilà, so this corresponds to this situation here. So you say, how robust is it? That is, if you take 40 winters, will you find the same?
Yeah. Or if you take a year, or if you take 2 winters.
If you take 2 winters only. Alors, if you take 2 winters, I don't think these numbers will be the same, but they should be 4 regimes, because this one corresponds to anticyclonic blocking over winter, which is always associated with pollution accumulation. This one corresponds to a situation where, on the contrary, it's raining and you have a strong wind, which can be channeled into the west branch in particular. There is a very strong wind, channeled wind, when there is a storm in Grenoble. And the 2 others, I would say, are the complementary. So I would say that if you consider 1 winter or 2 winters, very likely this threshold will be shifted. If you assume that there is one winter with nearly no anticyclonic regimes, which is rarely the case now, but so I would say this decomposition will hold, but this linear threshold will be shifted, will not be the same. Yeah? And this is what I would answer. This is what I answer.
So you'd still get your 4 regimes, but maybe the lines would be different, the limitations would be different.
Oui, c'est ça, indeed. Because the lines were really based on the data, of course, but they're based on this decision tree algorithm, and they were based so that you minimize the intra-cluster variance. So clearly it depends upon the number of points with a high value of PM10 you have. So it will indeed, this threshold will depend upon the winter you consider. It should not depend very much upon the winter. I mean, having a threshold for the anticyclonic regime, I lost the mouse, of 1020 hectopascal is something quite reasonable. I do not expect for a winter to have something much slower. And the same, I would say, having at temperature gradient, I mean, a little above -3 Kelvin per kilometer. This is something reasonable also to separate a regime with high stability from a regime with a low stability. But it would be quite interesting to maybe Enzo did it, but it would be quite interesting indeed to investigate. Again, since we used the word variability, the variability of this threshold to the winter you consider. And I would not expect big change, I would say, a big variance across this mean value, if I can say.
Thank you. We have a quiet group. I can ask another question. In examining all of the observations that you have on hand, have you noticed a change in the local circulation in terms of frequency and severity? So I'm trying to sort of tie the local study of air pollution to sort of a more climate scale type of scenario.
I do not understand your question. Can you repeat?
When you look at when you're looking at your meteorological data and you're dividing them into these pollution regimes, over time, have you noticed a change in the local circulation in terms of frequency and severity? Are there more clustering? Is there more of a tendency over time to cluster towards one regime more so than another?
It's difficult to answer this question because here what are plotted are all the points. It is every hours of 7 winters. And the idea is to get a global approach in order to decompose into the statistical approach. In order to decompose into pollution regimes. So then according to what you say, you have to look, you have to investigate how this figure is constructed. And I would say over time is something we are not interested in, because we are interested in the in having a large database consisting in many points, over which, I repeat, you can do some statistical analysis, like applying this classification. So it may be useful to look winter to winter. What can I say? For instance, now, again, there is an anticyclonic regime over Grenoble. So the points all gather, of course, in this gamma PT regime. But at the end of this regime, say the pressure will still be high, but I would say it's the opposite. That is, at the end of this regime, when the pressure starts dropping, it takes some time before the stability decays. So we move. I lost my mouse. So we lose from the gamma PT regime to the gamma T regime. You can understand this regime like this. And conversely, at the beginning, considering again the anticyclonic regime because it's here. Again, when the anticyclonic starts to form, so the pressure is high, so we are in the gamma P regime, but the stratification is not built yet. So I would say that the gamma P regime corresponds to a phase preceding the establishment of an anticyclonic regime associated with stability, and the gamma T regime corresponds to the end of the anticyclonic regime. And this was shown by Enzo, and that the pathway is actually this one, from gamma P to gamma T. And once the pressure has dropped, then the stability progressively decreases, and maybe I would say the stable gradient is completely destroyed, and you move to gamma zero. So the evolution over time I can discuss about, I would say, is this one.
Thank you. That's another science question to be answered at another time. We have a question from Carol Costanza, and she says, excellent talk, Chantal. For the 3 areas you found with the highest PM concentrations within the valley, in the last section of your talk, are there plans to put observation systems in those exact locations?
Oui. No, she's fully right. Thank you, Carol, for your message. Yes, indeed. This is not planned yet, but it's clear that we should do that. Actually, we have been discussing with colleagues interested in atmospheric chemistry, and they are part of the Mobilair project. We are part of also, and they, before putting measurements there, and I understand this concern, they would like to be sure that these hotspots actually also exist during other type of pollution regime, like the gamma P regime, like the gamma T regime. If you have a wind coming from the south, for instance, though we try to be to not focus on the synoptic wind, as you understood, because we were interested in pollution regimes. But I mean, is it occurring more than during a wintertime anticyclonic regime, or is it more general than that? From my point of view, it's more general than that. Maybe I can share my screen again. I think it's more general than that, because when you are, maybe I should leave. No, that's okay. Voila. When you are here, it's I should escape. Well, when you are here, the reason for which you have a hotspot here is because, as you can see, the wind is down valley here and down valley again here. So from this point of view, you can quite understand that there is a recirculation zone here. And as well, the wind flows from here. So this zone is a recirculation zone, which is associated with a strong pollution. In the same way, when the wind is flowing, is flowing like this, it's the main, I would say, trajectory is this one. So this region here is it's not a cavity, but it's exactly as if you were having a cavity. So there, in this situation, you expect indeed, small circulation zone to occur there, and the pollutant to be trapped. So I'm not surprised, about these hotspots. So I think we should convince people that they do occur for other regimes in order for measurements, air quality stations to be put there. But I'm thinking, and in this situation as well, we can understand because the air is blocked actually, so the flow cannot escape. This is a small topography there. So the reason for which, and there are industries in this small valley, so we understand that there is pollution there. There is no air quality station. I was told that in order for the measurements to be trusted, I would say at national and European level, you should have a sophisticated and air quality station whose cost is something like 70,000 euros. So I quite understand that the Air Quality Agency are not ready to put measurements there. But now, as you know, there are microsensors. So I think it would be which are not expensive. So it would be extremely interested to provide people who are living in this place here microsensors, maybe not telling them that they are living in a polluted place, telling them that we would like to measure the air pollution in Grenoble outside, I would say the main part of the city, and it would be very, very interesting to get measurement there. By equipping, as you understand, people with microsensors. So thank Carol for a question.
Thank you, Carol. It looks like we are past the seminar hour. If you are interested in Professor Chantal Staquet's presentation and have further questions, please reach out to her via her email, which is provided on the seminar flyer. On behalf of NCAR and EOL, I would like to thank Professor Staquet on her excellent presentation, her and her students' excellent presentation on the meteorology and general circulation over the Alpine Valley region of Grenoble. Thank you, everyone, and have a good day.
Yeah, thank you very much for your invitation.